Now, let's revisit the salt brine problem. You remember, in last lesson, we have a tank hold 1,000 liters of brine solution, and it flow in with 4 liters per minute. The concentration is 0.2 kilograms, and the flow out at the same speed, and then the concentration we know is the total amount of salt divided by the volume, and that's the question. We solved it. And then we say we are done because we are undergraduate students. We are done, give it to the teacher. But now, no, we are not done. We finished halfway. We got the mathematics model, which is a first order linear differential equation with the initial condition. And we provide you the solution. How do we solve it? Give me 10 minutes, I can solve it by calculus 2. That's not my focus today. And we answered the question. That's all have done last time. And so the first thing is, how do you know? Can you convince me you're right? Okay, if I don't know math, can you still convince me you're right? So first thing, verification. That's not too hard. You can take the derivative of the solution and plug in back into the original equation, and you can solve it. That's what you learned. You know, this is solution. You take the derivative and put on the left, and you compare to the right. If it is right, good. So verification is not new. Sometimes, unfortunately, we only get the numerical solution. You cannot plug it in. There's nothing to plug it in. No formula. So verify is a little bit harder, but we have a all standard method to do it. So validation is what I concern. So first, what you observed. You observed in the beginning, the density is 1 kilogram per liter, and then if you let the t equal 0, you suppose to get 1,000 kilograms of salt. Hence, the concentration is precisely 1 kilogram per liter. That's again unrealistic. Look, when you put the t equal 0, look how much you get, 200. E to the 0 is 1 plus 800. That's exactly 1,000 kilograms of salt. And your volume is 1,000 liters. And then you divide, you get 1. And that's the concentration in the beginning. That makes sense. Okay. You check the one thing. And what else you can check? Oh, you can check because the flow in has a less density than the inside, which is 1 kilo per liter. And this water, the brine, would dilute the concentration of the salt inside. When I say dilute, you understand that means the density, the concentration will become smaller and smaller over time. And also you observed, in long term, all this original 1,000 kilograms of salt was purified out, flushed out. And whatever you float out, in the end, when t goes very long time, you call it infinity mass, should be also 0.2 kilograms per liter, just like what you flow in, right? So those are the observation. You use it for validate. Now look again. E to the negative t to the function is a decaying curve. It's like that. Goes to 0 when t go to infinity. that justify your solution will be smaller and smaller and smaller. That's the word that we call it dilute. Next, you take the limit t go to infinity, that one go to 0, and then you got 200 kilograms inside of the tank. And you divide the total volume, which is 1,000. What you get is precisely 0.2 kilograms per liter. That's what the concentration of the brain flow in. That's exactly right. So those kind of things, even it's simple, but they give you the idea how we are going to justify our answer. And then you validate your model. Next, we need to go to the 3 assumptions. So what are the 3 assumptions? And we say it is observed for long-term trend. That means the t goes from 0 to infinity. That's pretty much artificial, just to try to make it as a mathematics model. Second, we make the assumption. What assumption we made? We made the assumption the concentration flow out equals the total salt divided by the total volume. What does that mean? That means here you have unified the concentration, the mixed very well. Then how do you know that? Oh, that the keyword is well stirred. It told you that it is well stirred. That's important. That justifies your second assumption. And the third assumption, oh, where your equation come from? What is your first principle? Oh, the first principle is the material invariant. It does not come free, does not go away. It just comes from the input minus the output is the first principle. The change equals input minus output. That's exactly what we call it compartment analysis. So the third assumption is also justified. Well, now you explained your answer, you justified your assumption, you checked your units. Oh, how do I check my unit? You look both sides. The unit is liters per minute, that the speed, are times kilograms per liter, that's the concentration. And then you cancel it out of the liters, and then what you left is a kilogram per minute. That justifies your unit of dx dt, which is kilograms per minute. And the input-output are the same. That is important for your validation. Dr. Andy Ledoux and I observed the shortcoming and the challenge of undergraduate research. And we observed, just as students are students, and if they solve the problem, they have no clue to see, have I done it right? How do I know I'm right? And then leave to the teacher. The reason is, of course, the training of your textbook and your subject. So you don't have the domain expertise. And so you cannot connect the mathematics tightly with your real-world application. And that's very common. Now, back to the example I have here.